So let's take a look at arc length. We can define arc length just by having a function right here. And let's just draw a curve. So our curve is going to go from the point A right here to the point B up here. And what arc length tackles is how do we measure the length of this curve? We can't just use a ruler to gain an accurate measurement because it's a function. That just doesn't work. So what we can do is we can take different tiny approximations or subintervals of our function. And let's just label this one x sub of I minus 1 and this point right here x sub of I. So that would make these 2 points up here p sub I minus 1 and this point right here p sub I. And what our arc length formula does, it takes this approximation of this line right here, this line to here, and so forth. And we take these approximations as this interval decreases, it goes to 0. So we can just rewrite this whole idea or concept of what we're doing as the limit as n approaches infinity of the sum as I goes to 1 to n of the distance between the point p sub I minus 1 and the point p sub I. So when we take this limit, we're going to be given arc length, which can just be defined as the integral of a to b of the square root of 1 plus the derivative of our function, so f prime of x, and we'll have that squared. And then our dx. So this right here is our arc length. So now that we know what our arc length is, let's look at an example problem. So find the arc length, we'll just call it capital L to save space. Find the arc length of the semi-cubical parabola y squared is equal to x cubed between 1, 1 and 4, 8. So for the first step of this problem, I would say let's define our y function, y squared is equal to x cubed, in just terms of 1y. So right now it's y squared. Let's just get it to y. So we can just square root both sides to get y is equal to x to the 3/2 power. Okay. So now we have our function. Let's write our arc length. So remember, our arc length is going to be equal to the integral from a to b of the square root of 1 plus our derivative of our function, f prime of x squared dx. So now that we have our y, let's find our y prime. So y prime is just going to be equal to 3/2 x. Since we're using the power rule, we just take that 3/2, move it down, and then 3/2 minus 1 is going to be equal to 1/2. So we have 3/2 x to the 1/2 power for y prime. And now with this, we can plug it in to our arc length function. And our bounds, remember, from a to b, so 1 and 4. So 1 to 4. And then we're going to have the square root of 1 plus 3/2 x to the 1/2 power squared dx. Now let's make some room. And now we can start evaluating our integral. So as our integral goes from 1 to 4, and 1 plus 3 halves x to the 1/2 squared, and then for the 3 halves x to the 1/2 power squared, we're just going to square every value. So we'll have 3 squared over 2 squared times that square root of x squared. And when that simplifies, we're just left over with 9/4 x dx. And now we're just going to combine like terms inside of our square root. And to do that, we'll convert the 1 to 4 over 4, so we can have common denominators, plus the 9/4 x dx. And now since we have this 1/4 in the denominator for both of them, we can pull out a 1/2. Because a 1/2 squared, when it goes inside the square root, will become the 1/4. So we're just factoring that out from the square root. And then on the inside, we're left with 4 plus 9x. And then dx on the outside. And from here, now we can just use our u substitution to evaluate the integral. So if we let u equal to 4 plus 9x, the derivative of u is going to be equal to 9. 4 is just a constant, so it doesn't go into anything when we take our derivative, and 9x, using the power rule, just becomes 9. We'll have dx. In our integral, we just have a dx at the end. There isn't any other variable attached to it, so for the du equals 9 dx, we can divide both by 9. And then we're left with 1/9 du is equal to dx. And let's also change our bounds. So if we plug in 4 plus 9 of 1, and I just noticed right here, 1 to 2 should be 1 to 4. So if we plug in our old bounds into our equation for what we substituted for u, we'll get our new bounds for our u substitution integral. So we'll have 4 plus 9 times 1, which is just 13. And then we'll have 4 plus 9, and we're plugging in our 4. And that will just leave us with 40. So that is our new bounds. So a, b. So if we plug this into our integral, we'll have from 13 to 40 of 1/9 on the outside. We still have that 1/2 on the inside of the square root of u du. And now let's just make some room so we can do our final steps for integration. It'll be pretty simple. All right. So let's take that 1/2 out. So we're left with 1/18 of 13 to 40 square root u du. As we take this interval, as we evaluate this integral, we're going to be left off with 1/18 times 2/3 x to the 3/2 power, going from 13 to 40. And now let's just multiply the constants that we have. So 1/18 times 2/3 will give us 2/54. And then we have our x to the 3/2 going from 13 to 40. The 2/54 will reduce to 1/27. And then we'll have 40 to the 3/2 minus 13 to the 3/2. And in math, they don't really like us having our final answers with the 3/2. So we can just always remember 3/2 is the same thing as just the number by itself times the square root of that number. So we'll have 40 square root 40 minus 13 square root 13. And that is our arc length.